Good afternoon, everyone. This is Han Hu from Microsoft Research Asia. In this tutorial, I will talk about self-attention modeling for visual recognition. There will be two parts in this tutorial. The first is to summarize the applications of self-attention models for visual recognition. Specifically, in these applications, there are three kinds of basic relationships to model, including pixel-to-pixel, object-to-pixel, and object-to-object. The second part is the diagnosis of self-attention models and its modeling improvement. I will introduce our recent study on it, mainly trying to answer two questions. Firstly, are self-attention models learned well on visual tasks? Secondly, how can it be more effective? Let's start the first part. Nowadays, visual recognition mostly follows this paradigm. Given an image, we first use a backbone network to extract the image features. It can be ImageNet, VGG, GoogleNet, or ResNet. Then, different head networks are used to process various recognition tasks. Here shows four kinds of recognition tasks, including image classification to produce a label for the image, object detection to produce all object boxes in an image, semantic segmentation to produce category labels for each pixel, and instance segmentation to further differentiate different objects when labeling the pixels. I take the object detection to show how it works detailedly. Given an input image, we first do image feature extraction to produce some feature maps. In this step, the main image operator is the convolution layer. It's basically about the modeling of pixel-to-pixel relationship. Then, we extract region features for each object proposal. For example, for these 5 regions of interest. Next step is usually achieved by the ROI-align operator, which can catalyze uniformly sampled image features within a box to form the object feature. This step is basically about the modeling of object-to-pixel relationship. The final step is to recognize each region by applying a small network on each object feature. In this step, the common practice is to recognize objects separately. However, object-to-object relationship could be also modeled to improve the performance. To summarize, for object detection or the more general visual recognition problems, there are mainly 3 kinds of basic relationships to model, including pixel-to-pixel, object-to-pixel, and object-to-object. These 3 kinds of basic relationships are usually achieved by convolution, by ROI-align, or without consideration. In this tutorial, I will show all these basic relationships can be modeled by a general model called self-attention. So what is a self-attention model? Please see this figure, which takes the objects as an example. For object, it transforms its input feature by encoding its relationship with other objects. The input and output features can have the same dimension, and therefore the module can be stacked anytime. The module interacts between objects by 3 projected vectors: query, key, and value. In computation, the output feature of one object is a weighted sum over the value vectors of all other objects, and the corresponding weight indicates the projected similarity between a query and a key, usually implemented by an inner product. The self-attention module has dominated the base architectures for the field of natural language processing, specifically by the transformer architecture from Google Brain. In this architecture, the self-attention modules are used to build dependency between tokens or language words. For computer vision, it's not that dominant, but it plays a strong competitor in modeling all kinds of these three basic relationships. Also, it's still quickly growing. In the following, I will introduce the representative works of self-attention modeling for these three kinds of basic relationships. We first review the usage of self-attention modules to model pixel-to-pixel relationship. Previously, the pixel-to-pixel relationship is modeled by convolution or its variants. The self-attention modules can be used to either complement or replace the convolution layer. In general, although powerful, convolution has its limitations. For example, the convolution layer is too local. It has difficulty extracting long-range pixel-to-pixel dependency. Please see this illustration. For this output, even by stacking 4 layers, only pixels within a short distance are modeled. Other pixels are not. Here is a pioneer work which applies self-attention models to encode dependency between distant pixels. Please see this figure. A football pixel and the human body pixels are distant from each other, but their dependency can be modeled by a single self-attention module. In this work, the self-attention modules are sparsely inserted into a ResNet to complement the local convolution layers. For example, this is a ResNet. In object detection, one block is inserted at stage 4 of the ResNet. The self-attention module can be also applied inside a convolution layer. This is a work on ICV 2019. Please see this illustration. This is a standard convolution. This is the self-attention module. The self-attention module encodes the global information to complement the standard convolution channels. Another issue of the convolution layer is its theoretical inefficiency. Please see this image. There are 3 boards with slightly different head poses. The convolution layer plays a template matching. It uses fixed filters across all image positions. It needs 3 channels to encode these 3 board heads, which is inefficient. Can we have better efficiency than the convolution layer? To this end, our paper on ICV 2019 employs self-attention layers to replace the basic convolution layers. Other than using fixed filters as in the convolution layer, the self-attention formulation can make the filters adaptive, with the filter width determined by composability of 2 pixels. In this way, potentially it needs only 1 channel to model different border head poses, while the convolution layer needs 3 channels. This self-attention layer can be used to replace all spatial convolution layers in a ResNet. The resulting network is totally convolution-free and is named LRNet. On ImageNet classification, this new network based on self-attention modeling performs 2.7 better than ResNet with the same computation budget. Note that ResNet gets the best accuracy at the kernel of 3x3. Please see the blue curve. And the self-attention network gets the best accuracy at the kernel of 7x7. Please see the orange curve. This result means self-attention can harness larger neighborhoods than convolution layers. Recently, these kind of networks have been improved to beat ResNet of different depths by a large margin. Such networks also show more robust to adversary attacks than convolution networks. We then review the usage of self-attention modules to model object-to-pixel relationship. Previously, object-to-pixel relationship is usually achieved by a RY-align operator. Self-attention modules can enable more flexible modeling and may also significantly simplify the pipeline. I will briefly introduce two related works. The first work is from our team, published on ECCV 2018. It uses a self-attention module to adaptively extract region features from image features of all positions. Compared with our align, it can adaptively extract information, and it can also encode context information. It demonstrates better performance than our align. The second work is from Facebook AI Research. Instead of using explicit region proposals, it uses implicit object orientations, which are automatically learned by network. This approach significantly simplifies the object detection framework. Next, we review the usage of self-attention modules to model the object-to-object relationship. Before the self-attention modules are exploited, the objects are usually analyzed separately. With the self-attention modules, we can process them jointly. There are many applications by this joint modeling, including object detection, video action regulation, multi-object tracking, and video object detection. I start from an example to illustrate the merit of object-to-object relationship modeling for object detection. Please see this patch. I believe it's difficult to figure out what it is by seeing this patch alone. However, if we see the context, it's easy to recognize the patch as a baseball glove after noting a baseball player is holding it. This is a work by our team, published on CVPR 2018. We use self-attention module to model relationship between objects. Compared to standard self-attention model, this module additionally accounts for relative position in the attention computation, which is important for visual applications. We apply it to object detection, which is the first fully end-to-end object detector. Concretely, the module is inserted into two steps of a faster RCN object detector. Please see the red blocks in this pipeline. Firstly, it's inserted in the instance regulation head. Now, the objects can be jointly recognized instead of processed separately as in previous methods. The second is to do duplicate removal. In previous methods, duplicate removal is usually achieved by a handcrafted no-maximum suppression method. By the self-attention module, we can make this step end-to-end learnable. This is the result on COCO. Note the baselines in the original paper are a bit out of date. We thus try the module on a stronger baseline, which gets 45 AP on COCO. On this strong baseline, the module can still bring 0.9 improvements. The modeling of object-to-object relationship can also take effect across image frames. It's useful for various video applications. For example, in ECCV 2018, a paper exploits this module to improve video action regulation. For another example, in SCV 2019, we apply it to improve the multi-object tracking problem. It can also benefit the problem of video object detection, where the main dataset is the ImageNet VID. Now, all top methods on ImageNet VID are based on self-attention models. In particular, we will present a method on this CVPR conference, which achieves the best accuracy on this dataset. If you are interested, please come to our poster, number 64, on Thursday. To summarize, there have been a lot of work using self-attention modules to model three kinds of basic relationships in visual regulation, including pixel-to-pixel, object-to-pixel, and object-to-object. The self-attention module is a strong competitor for many tasks. It's usually complementary to existing architectures. It's also a key component for the SOTA solutions in video analysis, and there is still much room to improve. Now we present the diagnosis of self-attention models as well as their modeling improvements. In this part, we will study two questions. Firstly, are self-attention models learned well on visual tasks? Secondly, how can it be more effective? The content of this part are mainly based on two papers of our team. The first is ImageNet, and the other is Disentangled the local networks. In common understanding, the self-attention formulation models pairwise relationship. For example, please this figure to model the dependency between pixel pairs. A natural question is, does it learn the pairwise relationship well? To learn meaningful pairwise relationship, we expect different query points affected by different key points. This is an illustration. The left image shows two query pixels at different locations. A red query is on a car, and a yellow query is on a fire hydrant. The right image shows some key pixels colored in green. We expect the car query pixel mainly affected by these two key pixels. And we also expect the fire hydrant query pixel mainly affected by these two different key pixels. But what does the self-attention module really learn? Actually, unlike expected, we find different queries in the left image are usually affected by the same key pixels in the right image. This means that the self-attention degenerates from query dependent to query independent. It behaves more like a Unary model instead of a Pairwise model. We also show some real examples from the tasks of object detection and semantic segmentation. These images are the attention maps of all key pixels to different query points, where the query points are marked by white crosses. And for the attention maps, the warmer the color is, the higher the attention similarity is. We can say that the attention maps of different query points are very similar, especially for object detection. This also indicates that the self-attention model degenerates to a Unary model. So, what causes the degeneration issue? To answer this question, we examine the formula of self-attention in depth. Please see this formula. We find that this self-attention formula can be divided into a weighted pairwise term and a hidden Unary term. We study the behavior of these two terms by learning each term alone. We surprisingly found that the unary term alone performs even better than the standard joint model, which includes both the unary term and the pairwise term. These results also indicate that the pairwise and unary terms are not well learned when combined in the standard self-attention formulation. We further analyze what kind of visual clue is learned by each term alone. The left two images are the attention maps learned by using the pairwise term alone, giving two different query positions. The right image is the attention map learned by using the unary term alone. Now we look at the visualization of pairwise term. We find that the pairwise term tends to learn the relations between pixels that have same category. Please see the first image. The query point locates at the sky area, and all sky area has high responses. And please see the second image. The query points locate on a car, and the car area shows high responses. Then, let's see what is learned by the unary term alone. We can see that the unary term tends to focus on the boundary pixels. It looks very similar to this ground truth boundary map. Such observations are also evidenced by statistical analysis. We count the correlations of the attention maps with the ground truth. This is the result. The diagonal numbers are high, indicating high correlation between pairwise attention maps and the pixel category map, and also indicating high correlation between the unary attention map and the boundary map. Then we compare these alone models with the joint models learned by the standard self-attention. These are the pairwise and unary attention maps learned by the standard joint model. We can say neither of them learn clear visual meanings of within category regions or boundaries. This is also evidenced by the statistical correlation with ground truth. The correlation numbers are much smaller than those learned alone. This result also indicates that the learning of visual meanings by a joint model is worse than that by the alone models. So, why is the joint model worse? We investigate the reason behind. We revisit this similarity computation. We notice that the two terms are combined by multiplication. We argue that the combination by multiplication is bad. Firstly, it couples the two terms in gradient computation. Please see these two backpropagation formulas for the pairwise and unary terms, respectively. The gradient of pairwise term is determined by the value of a unary term. Also, the gradient of unary term is determined by the value of pairwise term. This is bad for optimization because if the value of one term is small, the gradient of the other term will vanish. Second, multiplication acts like intersection. The intersection of two different visual clues will be empty and thus it's useless. Instead of using multiplication or the intersection, we try the union operation. By a union operation, no matter what visual clues are learned by the two terms, their combination will be their union, and will include both. The union function can be implemented by a simple addition operator instead of the original multiplication. By using an addition operator, the gradients of the unary and pairwise terms are also disentangled. On cityscapes, we observe 0.7 improvements by using addition to replace multiplication. And the visual meaning is also significantly clearer. Please see this illustration. But is that the end? Or are there other coupling factors? The answer is yes. There are still coupling factors. For example, we find the key transformations are shared in the pairwise and unary terms. We thus further disentangle these transformations by using independent key transformations. By these independent key transformations, the visual meanings are made clearer. Please see the right column. By combining these two disentangle tactics, we achieve about 2-point improvements over the standard separation models, and we achieve about 5 points improvements than the baseline without separation. We name this method Disentangled local networks. It achieves competitive or even better results with other SOTA methods in the mainstream datasets for segmentation, including cityscapes, ADE, and particle context. The disentangled local network is general, which can also benefit object detection, instrumentation, and action regulation. This is the visualization of the learned attention maps on object detection. The left shows the results by the standard separation models, and the right shows the results by the disentangled separation models. We can see for standard separation models, the attention maps of different query points are almost the same, indicating a degeneration to unary models. Well, for the disentangled separation models, the attention maps are learned to be different for different query points. On the action regulation task, similar observation is achieved. Well, the standard separation model is frequently degenerated to unary models. The disentangled separation model can effectively learn the pairwise relationships. To summarize, this tutorial reviews both the application and modeling views of applying separation modules for visual regulation. We first introduce the application view, where there have been a lot of works applying the separation modules to various visual applications, mainly to model the pixel-to-pixel, object-to-pixel, and object-to-object relationships. At present, the separation module plays as a strong competitor than previous solutions. It's usually complementary to existing architectures. For video applications, many SOTA approaches are built on this module, and there is still much room to improve. We then introduce the modeling view. There are two messages to take home. Firstly, the standard separation model is not learned well on many visual applications. Secondly, it can be improved by a disentangled design. That's all. Thank you.